Hi friends, let's have a look at problem 1722. Minimize Hamming distance after swap operations. So in this video, we're going to explain a solution based on the strategy split and comparison. So first, I'm going to digest the problem statement and the requirements, and then we analyze the algorithm, and finally we design the code. First, let's look at the problem digest. So here we are given two integer arrays. One is source and the other is target. They have the same length m. So we are also given an array called allowed swaps, where each element is a pair, let's say ai, bi, indicates that we are allowed to swap the elements at index ai and index bi. So of the array source, right? So note that you can swap element at a specific pair of indices multiple times and in any order. So the Hamming distance of two arrays of the same length is the number of positions where the elements are different. So here we want to find and return the minimum Hamming distance of source and target after performing any amount of swap operations on array source. So here we have three examples. The last one is very special because we can swap 0 and 4, 4 and 2, and 4 and 1, and 1 and 3. So we can freely swap all of them. So for the source, it actually is a set in some sense. It has unique elements. So 1, 2, 3, 4, 5. Target is also containing 1, 2, 3, 4, 5. So the output is 0. So this is example 3. This is very special, I would say. It does not catch the general case. So for example 2, because allowed swap is empty, so we cannot do the swaps. We can directly compare the Hamming distance. So we see the first position, both are 1, so same. The second position, different, count by 1. And the third position is different, so we count by 2. The last position, 4, 4, the same, so we return 2 for this one. And for the first example, I would say it's still not catching the general test case. So I'm going to specify this point when we do the analysis of the algorithm. So here we have 1, 2, 3, 4, and the target is 1, 2, 4, 5. So here we can swap 1, 0, 1, and 2, and 3. So here, 1, 2 indices corresponding to 1, 2 in both source and target. So if we swap once, we get 2, 1. So these two positions can be equal. So for the last two indices, 3 and 4, and 4 and 5, so we can make the 4 the same, but still the last position have 3 and 5. They're different. So we return 1. So this is the example 1. So before we do the analysis, let's also look at the constraints. So here I want to emphasize the length n, which can be as large as 10 to the power 5. So for all the other ones are just some consistency assumptions. We're not going to go over the items. So with that said, we finished the digest of the problem. So now let's look at the analysis of algorithm. So this will be the main part. I would say understanding the algorithm is the key for this problem, while doing the coding or design the coding is rather straightforward. So now let's look at the algorithm. I'm going to use example 1 as a demonstration, right? But I want to comment also on the general case. So we use three-step operations. So I start from step 0. We split the indices to clusters according to the allowed swaps, right? So for example, in the first example, 0 and 1, these two indexes are in the first group, 2 and 3 are in the same group. Notice that the indices are unique, so we can do partitions for these indices. So we get C1, let's call it C1 is 0, 1, and C2 and 0, 2. So this is step 0. Then in step 1, we are going to reduce the problem to comparison of two dictionaries. So these two dictionaries actually have elements and their counts, frequencies in other words. So in the first example, the source yield, so the first two elements of the source will be 1, 2. 1 appears once and 2 appears once. Well, in the target, the first two elements, two indices gives us 2 corresponding to 2 appears once and 1 appears once. So here the key is the element and the value is the frequency, right? So this is C1. Well, for C2, they are corresponding to indices 2 and 3. So the source gives us 3 and 4. So 3 appears once and 4 appears once. Well, in the target, so we get 4 appears once and 5 appears once, right? So now I want to check for the two clusters, how many elements we can make them the same or the equal. So for indices in C1, the number of elements we can make equal. So how can we do this? We pick the common keys and we sum the smaller frequencies. So this is the computation formula. For example, we have the common keys are 1 and 2, right? So we compute D1 1 and D2 1. We pick the smaller one. And then we compute the same for the K2. And then the first item is 1, the second item is 1. So we get 2. In other words, for this cluster C1, we can make 2 elements the same, right? So similarly for C2, the number of elements we can make equal. First, let's look at the common keys. So in this case, we have only one common key, that is 4, right? But 4 appears once in each cluster, in each of the 2 yielded dictionary. So the minimal will be 1. This is also the number of elements we can make equal. And then we get the return. So get the return, we just need to use the length of the source or equivalently the target. Then minus the element we can make equal. Minus 2, so minus 1. So we get 4 minus 3, that is 1. So that's basically the algorithm. It's very clear and very structured. So now the question is, why did we use dictionary in step 1, right? So here the thing is that the elements in the source or in target can be non-unique. This is also the point where all of the 3 examples are not most or very general, right? So this is the question. Our plan will be the following. For step 0, we can use UniFind to make these clusters. It's similar like finding the connected components in a graph, but this is very routine, right? You can use different methods, so this is just a choice. And in step 1, we can use counters and write a hyperfunction. So again, here you can do it in a different manner. And step 2 is the return. The return can be computed in different means, but still a lot of freedom. For example, here if you sum the values, so you get 1, 1. So that's the 1. So there's the same. So we get 2. So the numbers we can make equal is 2. So 2 minus 2 is 0. So for this one, the summation of frequencies for the dictionary is also 2. And we can make 1 equal. So 2 minus 1, that is 1. So you add the 0 and 1 together. This is another way of computing the return. But this way looks to me more clear. So we know the full length, and then we minus the elements we can make equal. The number of elements we can make equal. Then this is the return. So again, you have a lot of freedom. So the point is that the algorithm is the core. And we have choices when we implementing or design the coding format. So with that said, let's make a quick implementation of this algorithm. So here, let's use step corresponding to above, right? So step 0. So basically split the indices into clusters or groups, right? So here, this actually corresponds to connected components. If you want to make connections with the graph. So here we are mainly working with the variable allowed, the information allowed swaps, right? So for this, we can use UniFind. So first let's get in the length of the source. This is just for convenience. So the length of the source and the length of the target is actually are the same. So now let's write a roots. So here I just want to make some preparation for doing UniFind. So here for I in range n, because we are using 0 indexing, and rex. So here I want to give a full implementation of union by rank, and also with path compression in the fed. So I1 for I in range n. So in this problem, you can understand the 1 here in the rack is a cluster represented by the size of a cluster represented by, say, this key I. So now let's look at the method for fed. So function fed with path compression. So for this problem, I guess we don't need to use this strong implementation, but for general purpose usage, so we make it here. So define fed, give me an index so I can find its root. So first let me introduce a root I, right? And then let's use a while loop, while result and the roots I are not the same. Then we just, what we want to do, basically set results to be the parents. Then what we want to return is the result. Because after the while loop, so result and the roots of result will be the same, right? So, but in order to accelerate this a little bit, so we use path compression. So we can apply, or you can understand this roots as a operation. So we apply this both, right? So in other words, we set the roots of result to be the roots of a roots result. So this way, so here a result. Notice the typing. The typing is very important. So let me check this function. So we set result to be I, and then where result does not equal to roots result. Then we're going to do result equals its root. In other words, we climb up along the chain. So in order to accelerate a little bit, we apply roots to both sides of this one. This is the so-called path compression. There are different ways to implement path compression. Here we just provide you one format. So if you are interested in looking at more of the applications or different ways to implement path compression, you can check out my playlist for UniFend. So this is the UniFend. So that's the find method. Then the uni function with rack, right? By rack, sometimes called union by rack. So the function. So for this, let's see, define union. So we get two indices, ij, right? So first, we are going to get the root of the two indices. So let's just use the fend because we have just implemented it. Fend g, right? So what we want to do is that we check if the two roots are the same. If I and j are already in the same cluster, it means that their roots are the same. So we do nothing. Otherwise, we just do union. So if root I does not equal to root j, then what we are going to do? So we check the rack. So we want to set the root of the smaller rack to be the larger root. So basically, if rack's root I is no less than that of root j, so here we are going to set the roots of root j to be root I. That's what I just said. And then we increment the rack of root I, increment by that of root j. So it means if you have a larger size, you are going to absorb the smaller ones, and in combination with the path compression, it actually accelerates the check. For example, given the index, I want to find its root or its cluster. So this will be accelerated. So if it's the other direction, so we do the same thing, but in the reverse direction. Let me copy this part and made some modifications. So here we set the root of root I to be root j, because root j has larger rack. then we increment the rank of root G by that of root I, right? So that's the union by rank function. So this part is the so-called union by rank. But if you do not do this, this is also fine in this problem. You just directly set, say, the root of root G to be that of root I. That's it, right? So basically, if you do not do this, then you just set root of root I to be root G, or in the other direction. Then that's done. This is a typical vanilla union function. But here, let me delete this, and I do it by rank. So with that said, so we finished the implementation of the find and the union method function here, because we didn't use a specific class. So now what we are going to do, so let's do another function. Let's see, just a hyperfunction to get clusters or connect components. So here let's define it as get clusters, right? So here we're going to have a dictionary. Let's use this implementation. So here we can write one line implementation, but we want to expose to you some details. So here for IDX and P in root items. So first I want to get, so here is the index. We know its parents, but we want to assign using the cluster name or the root. So the root will be find P, right? Then we're going to check if root in D. So what we're going to do, so we're going to root, not root, so D root. So I'm going to add the index to the corresponding cluster. Otherwise, root is not in D, so we're going to set D root equals a single element set at the present time. So we are going to return D, right? So this is our implementation. So here, so we have find function, unit function. We have another function is called get clusters. And then let's look at the problem logic. So I'm going to do unit operations by looking at the allowed swaps. So for ij in allowed swaps, so what we are going to do, we just do union ij, right? So this will ingest all the information contained in allowed swaps. So I'll regard this one as step 0. So next, let's look at step 1. So step 1 actually reduces the problem. Problem reduces reduced to the following. So let me write some detail. So what we are going to do, within each indices cluster, right? So we count the number of elements, or we can make equal, right? So this further is reduced to comparison of two counting dictionary or two counters. So now let's specify this. So here, in order to write it in a verbose way, I'm going to write a function to do this. So what I'm going to do, I'll get common, right? So given D1 and D2, two dictionaries. So the two dictionaries are counters, or just the general dictionaries. So it's count element and frequency. So the requirement as assumption, assume that D1 and D2 contain same number of elements. So here we with counting multiplicity or frequency, right? So in other words, we just need the values summation and to be the same number, like here, right? The values summation the same. So this is 2, this is 2, right? So this is very simple, right? As we mentioned here, we are going to pick common keys and sum the smaller frequency. So let's see if I just need to iterate for one dictionary, right? So let's say result equals 0. So the result will counting the number of common elements we can make equal. And then for k in D1, right? So if k in D2, right, it means a common key. So we're going to increment the result by minimum of D1 key. So because k is already in D1, this is reasonable, and D2 key, right? So actually you can also use the get method with default value in dictionary if you like. So dictionary get the key and then default value. Typically the use case is like we search a k, d, let's see, get, see the k is 1, right? If 1 is not inside, we're going to set it to be 0. So this is general use pattern, right? So then we are going to return the result. So now with those functions ready, so let's look at step 2. Step 2 is get the return, right? So for each cluster of indices, so we call the above function get common function, and then we get the number of elements we can make equal. Then we use the total length of the source minus those numbers, so we get the return. So first let's get the clusters. So this let's call get clusters, right? So notice that we call this function after we do the problem logic, right? Do the unit operations. So now let's do, so the number of elements we can make equal, let's call it n equal, initially 0. Then we iterate over the clusters. So for C in clusters, so we are just interested in the sets or the values, not the name of the cluster, right? So we got D1 is, let's use a list comprehension, collections counter, right? So then we find the elements corresponding to those indices in C. That is source I for I in C, right? Then D2 is the same, but we compute using target, right? Counter. So let's use comprehension again. So we get target I for I in C, right? So these are the two dictionaries we're going to call for this get common method. So now let's see in common. So the number element we can make common corresponding to the current cluster C. That is get common, right? D1 and D2. And then once we get this, and then we get n equal, it's incremented by n common, right? For sure, you can combine these two lines as one line, combine these two lines as one line, but without introducing the n common variable. But the reason we write like this way is to expose to you the details of sort process. So now we have all the information. So after this for loop, we know how many elements we can make them equal. That is n equal. So what we just return is nothing but length of the source, that is n, minus n equal. So that's the whole part. So before we make any comments, let's first do a test. Yeah, it passes one example. Basically, it tells us our typing is no problem. So now let's look at the generic case. Yeah, it passes all the cases. So that's basically about the solution to this problem here. Now let me emphasize several points. The first point we want to emphasize is that the algorithm is the core of the key. Well, once we realize the algorithm, we can do different implementations, right? Depends on what we like. For example, do the splitting. So here I used unifund, but you can use different ones. For example, you can use traversal, reinterpret the allowed swaps as a graph, right? That's also a typical method. And then in the second step, so I implement a simple utility function to do the job. You can do it in a verbose way. And also, lastly, we can compute the output in different fashions. We can use minus, we can use plus. So we count how many elements we cannot make equal within each cluster, then we sum. So that's related to the first major comment. Another comment is that in this problem, if we analyze the 3 examples, I found that they're not so representative, I would say, or so general. So it's corresponding to the case in step 1, because elements are allowed to repeat, right? So that's why here we are using dictionary, not a set or general list. So this usage determines basically how we compute how many elements we can make them equal. So that's mainly regarded to the second major comments. So with the 2 comments shared, I guess that's about it for this video. If you like our video, you're welcome to check out other problems in our channel. And for this problem here, I implement a unit fund. So this is not necessary at all. Like we can use vanilla fund, we can use vanilla unit. But here I used union fund with path compression and union by rack. It's just to expose to you more knowledge or more technique. So you can also look at different application cases for the union fund technique, also known as disjoint set technique or data structure in my playlist. So we have a playlist in our channel called union fund. So it's actually nice to check out. So with that said, I guess that's it for this video. Thank you.